In this video, we're going to look at the National Research Council's Red Book paradigm. This was the very first risk assessment model, and it's worth looking at to understand the history of risk assessment. We have a few modest learning objectives for this video. At the end of it, I would hope that you could identify the steps of the Red Book risk assessment paradigm. You should be able to discuss the extrapolation issue for dose response curves. You'll be able to define a unit risk and identify some strengths and weaknesses of the approach as demonstrated in the example that will follow. The report summarized here is Risk Assessment in the Federal Government, Managing the Process. Let me read from the transmittal letters so that you have some background on this report. This study was authorized by Public Law 96-528, and it was carried out by a committee of the National Research Council's Commission on Life Sciences. This was done with support from the Food and Drug Administration. The Congress made provision for this study to strengthen the reliability and objectivity of scientific assessment that forms the basis for federal regulatory policies applicable to carcinogens and other public health hazards. Federal agencies that perform risk assessments are often hard-pressed to clearly and convincingly present the scientific basis for their regulatory decision. In the recent past, for example, decisions on saccharin, nitrites in food, formaldehyde used in home insulations, asbestos, air pollutants, and a host of other substances have been called into question. The report recommends no radical changes in the organizational arrangements for performing risk assessments. Rather, the committee finds that the basic problem in risk assessment is the incompleteness of data, a problem not remedied by changing the organizational arrangement for performance of the assessments. Instead, the committee has suggested a course of action to improve the process within the practical constraints that exist. And that ends my reading from the transmittal letter. So basically, this report was to determine whether organizational and procedural reforms could improve the performance and use of the risk assessment in the federal government. The report went on to define a risk assessment model that became the basis of many of the models still in use today. This report is often called the Red Book because of the color of its cover. This 1983 report defined risk as a characterization of the potential adverse health effects of human exposures to environmental hazards. It also defined risk as the characterization of the uncertainties inherent in the process of inferring risk. The process defined by the Red Book was essentially a human health cancer risk assessment technique. Risk assessment was defined as a process comprising these four steps. First, hazard identification. Second, dose response assessment. Third, exposure assessment. And fourth, risk characterization. In the following slides, we'll take a look at how the Red Book defines each of these steps. The definitions you see in this slide and the next couple of slides are taken directly from the Red Book. Hazard identification is defined as the step that is taken to determine if exposure to an agent causes an increased incidence of an adverse health effect. The dose response assessment characterizes the relationship between exposure at different levels or doses and the incidence of the adverse health effect of that agent that has been proven to cause an increased incidence of adverse health effects. In the exposure assessment, assessors would measure or estimate the intensity, frequency, and duration of actual or hypothetical exposures of humans to the identified agent. In the fourth step, risk characterization, assessors would estimate the probability of specific harm to an exposed individual or population based on the information from the dose response and exposure assessments. The Red Book risk assessment paradigm was originally designed to address carcinogenic chemicals found in the environment. Since that time, it has been widely applied in many different applications. The example that we're going to use will actually be a microbiological application of this risk assessment model, originally designed for chemical risk assessment. The example we're going to use is the Exxon Valdez oil spill, which occurred on March 24, 1989. As a result of the spill, native Alaskans were concerned that the spill may have contaminated their seafood. The Alaska Oil Spill Task Force requested a cancer risk assessment of the Food and Drug Administration in 1990. In the following slides, what I'm going to do is give you one small, simple example taken from a much larger and much more complex risk assessment. We begin, as always, by defining the problem. In the aftermath of the Exxon Valdez oil spill, the problem was to assess the risk of developing cancer from exposure to polynuclear aromatic hydrocarbons, which we're going to be calling PAHs from now on, if Alaskan residents consume molluscan bivalves collected from the oil spill area. Now that's the little tiny slice of the problem that we're going to be looking at. Actually, they were looking at the risk of developing cancer from exposure to PAHs from all sorts of seafood, seals, salmon, a wide range of different foods and animal species that were affected by the spill. But to keep this problem tractable, we're just going to focus on molluscan bivalves. Hazard identification is the first step in the risk assessment process. And remember, risk assessment is a science-based process, so we're interested in accumulating some evidence to support the hazards that are identified. So there are some reasons for considering PAHs. First, exposure to PAHs in animal trials show increased incidence of cancer in animals. Second is biodegradation. PAHs are very hydrophobic and they are resistant to microbial degradation. Bioaccumulation is an issue as well. The mollusks that are affected by the oil spill have difficulty metabolizing PAHs. They have no ability to move from polluted areas, and they come in contact with sediments where components of the oil accumulate. And then, of course, humans consume mollusks. So, to summarize the science, PAHs are harmful at low doses. They are the most likely of all components of crude petroleum to be passed through the marine food chain, and they have been associated with an increased incidence of cancer in animal studies. Therefore, the hazard is human exposure to PAHs. The second step in the Red Book risk assessment framework is dose-response assessment. There are different sources of information for dose-response relationships. They may be developed from animal bioassays, from human feeding trials, from epidemiological data, more recently from cell lines or tissue cultures. But animal studies have been most frequently used in the past, and animal studies are what we're going to be looking at in this example. Now here's a very brief and superficial summary of what an animal study is. You administer high doses of a chemical to relatively small numbers of animals, and then you record the percent of the animals that have an adverse health effect. There are a couple of issues with animal studies, and that is there's an absence of data in the low dose regions, simply because you feed the animals high doses in an effort to force adverse effects. Because we use animals, there's an absence of data for humans. These two features create an extrapolation problem that you'll see when we move through the coming slides here. There is no basis for choosing the best mathematical model to address that low dose range. Usually what happens is after conducting a couple of studies and getting some dose response points, you would fit a curve to the data that exists. Then, in most instances, analysts use a simple linear extrapolation to the 0 point from the fitted curve or its confidence limit. In the next slide, we'll demonstrate this. An animal study may be used to produce an actual data point. Each point has some administered dose and its corresponding response rate. Doses are often measured as milligrams per kilogram of body weight daily for a lifetime for chemical exposures. For microbes, they are usually a number of cells or colony-forming units. The response for a chemical could be the increase in the number of tumors over background rates, or for a microbe, they could be the probability of illness. Usually, there are a limited number of studies, and the doses represent a limited dose range that does not include low doses. A curve is statistically fit to the data points. I've used a straight line because I didn't know how to use an actual curve in this software, so don't read any significance into the linear curve I used. Because the curve is generated from a sample, the upper confidence limit of the curve is often estimated. The extrapolation problem depicted here is what is the dose-response relationship in the low dose range. This is important because humans are usually exposed to doses in the low dose range. There's no way to know with certainty what happens in a dose range that was not investigated, and the uncertainty is complicated by the fact that we are interested in the effects on a different species, humans. This problem is frequently handled by using a linear extrapolation from the upper confidence limit to the origin. Using the origin as a terminal point requires us to assume a no threshold limit. In other words, one atom of a chemical or one cell of a pathogen is assumed to be capable of causing the response of interest. The dose-response assessment in our example is slightly complicated by the fact that different PAHs are present in a single exposure source. So all the PAHs are compared to a single PAH, benzopyrene. The literature was reviewed for cancer bioassays of benzopyrene, and at the time, this risk assessment, which was being completed in real time because people were waiting to know if it was safe to eat the food in their area that they use for a subsistence diet, one study was found. It was a rat study by Brun et al., and it was dated in 1981. So this was the data that was available. Here's the dose-response relationship that was used. Take a moment to look at the dose. The dose is of benzopyrene equivalents. It's measured in milligrams per kilogram of body weight daily for a lifetime. The vertical axis, the response, is the proportion of rats developing tumors. The study revealed one data point. 0.11 milligrams per kilogram daily lifetime dose of benzopyrene is shown in the graph. A red line is drawn to extrapolate from the data point to the origin. The slope of this line is called a unit risk, and it is equal to 1.75. Just what does this 1.75 mean? The unit risk is simply the slope of the line that you just looked at. If you haven't thought about slope for a while, it was defined as rise over the run. In this case, the slope, the rise, was 0.18, and that's the proportion of tumors, and that's divided by the run, which is 0.11 milligrams. If you use those numbers, you would get a 1.63. I point that out because there are always people who would like to be able to duplicate the numbers from the graph, and you simply can't do that because of rounding. So we're going to be using the 1.75 as a proportion of tumors per milligram. So a unit risk means that for 1 milligram of benzopyrene, we have a proportion of tumors equal to 1.75 per milligram of benzopyrene. Please note before we leave this slide that the actual dose was far less than 1 milligram. But standardizing these potencies and talking about a unit risk, meaning a full milligram, is pretty standard procedure. It's easy to get confused about what this number means. Most people like to interpret a proportion as a percentage. 1.75 means 175%. But to say that 175% of all rats get a tumor is a nonsensical thing. So remember, a proportion is not exactly a percentage. As a ratio, it means there are 175% as many tumors as rats, and on average that means that rats would have 1.75 tumors for every rat exposed to a 1 milligram dose of benzopyrene. Now what we are after is the equation of that straight line extrapolation that you saw, and you'll see it again in just a moment. If it's been a while since you've thought about straight line equations, usually we use the equation y equals mx plus b. M is the slope, and in this case the slope is 1.75. B is the intercept, and in this case the intercept is the origin, is equal to 0. So if we substitute these values, we have a very simple equation. Y equals 1.75x. Now we are interested in a very low probability of cancer. 1 chance in a million. 1 chance in a million is 0.000001. Don't be confused by the bullets here. Unfortunately, the bullets show what is a dash that is not a negative sign. So we have 1/1,000,000th equals 1.75x. If we solve for x, we get the amount of benzopyrene that causes 1 chance in a million of cancer. And that amount is 5.7 times 10 to the minus 7th. This is basically the acceptable daily intake, also known as the ADI. So here's the extrapolation. We just calculated the equation for this, y equals 1.75x. We substituted in a value for y, 10 to the minus 6th. So imagine that we could very precisely locate 10 to the minus 6th on the vertical axis. And when we move on over to that red line to the curve and drop a perpendicular onto the horizontal axis, that's when we would get 5.7 times 10 to the minus 7th. And that is equal to 0.57 nanograms per kilogram daily for a lifetime. We've covered quite a bit in the last few slides, so let's summarize this dose response. We had one data point and a no threshold assumption. That enabled us to draw a line. We then calculated the equation for that line, and we were able to calculate a 1 in a million lifetime upper bound risk in rats that was interpolated from the curve. It's equivalent to 0.57 nanograms per kilogram body weight daily for a lifetime. If we have a 60 kilogram person, and that was the size of a person that was used in the Alaskan Peninsula, then 0.57 nanograms per kilogram times 60 kilograms tells us that as long as a person consumes 34 nanograms of benzopyrene daily over a lifetime, or less, their chance of cancer as a result of consuming benzopyrene is smaller than 1 in a million. If they consume more than 34 nanograms daily, then their risk of cancer associated with that exposure is greater than 1 in a million and would presumably be unacceptable. Now we move on to the exposure assessment step in the Red Book risk assessment framework. Here we're interested in estimating the amount of PAH contaminated food consumed and the concentrations of PAHs in that food. So the average daily intake of bivalve mollusks, according to a survey of Chenega Bay, Alaska, is 2 grams per person per day. Please note that 2 grams per person today is an extremely small amount of bivalve mollusks. This was an average daily intake, so clearly if people are not eating bivalves every day, the average could be quite small. In the actual risk assessment, there were volumes of food greater than 2 grams per person considered, as well as other foods. But as I mentioned earlier, we are using a very simple example, a very thin slice of the entire risk assessment, to demonstrate how it was done. So we will be using 2 grams per person per day. Given the amount of food consumed, the next step was to estimate the concentration of PAHs in foods. As mentioned previously, there's more than one kind of PAH, so all the PAHs found, those 3 identified in the bullets here, were converted to benzopyrene equivalents. PAHs and mollusk samples from subsistence fishing grounds in Alaska were used, and the mean level of PAHs in a mollusk was found to be 30 parts per billion of benzopyrene. Now we're ready to calculate the lifetime exposure dose. The units we're using aren't going to be familiar to everyone, so don't be too concerned about that. It's a very simple multiplication. We take the intake of mollusks, 2 grams per person per day, times the PAHs in mollusks, 30 parts per billion, and that gives us the dose of PAHs. That is 60 nanograms of benzopyrene per person per day. 60 sounds bigger than 34. The fourth and final step in the Red Book risk assessment paradigm is risk characterization. This is where we compare the actual exposure to PAHs to the 1 in a million risk that was calculated earlier. So for a 60 kilogram adult, extrapolating from those animal studies, we found that you have less than a 1 in a million risk if you are consuming less than 30 nanograms per day over your lifetime. Alaskans consume 60 benzopyrene nanograms per day. So the next question is this exposure higher than the advisory level? Is 60 bigger than 34? One would certainly think so, but in risk assessment you can never be sure. Prior oil spill data suggest that after 10 years the environment returns to its pre-oil spill status. That would mean that people will not be exposed to a lifetime dosage of 60 nanograms per day. So in this particular risk assessment, what the FDA did was as follows. They assumed that the exposure to benzopyrene would last for 10 years of a 70-year lifetime. So 10 years out of 70 is about 0.14 or 14% of a lifetime. 0.14 times 60 nanograms per day is equal to 8.4 nanograms per day. So FDA said the exposure to 60 nanograms per day for 10 years in Alaska is equivalent to an average exposure of 8.4 nanograms per day for a lifetime. This then is less than the 1 in a million risk of 34 nanograms per day. There are advantages of this cancer risk assessment. You can make a relatively quick determination of the significance of the cancer risk from exposure to a substance. You can compare unit risks for cancer for different compounds. Recall that the unit risk here was 1.75. The process is consistent in its data requirements and its use of a 1 in a million risk. The process is not without its disadvantages. There's a large uncertainty due to the low dose extrapolation and applying exposures and health effects determined in animals to human beings. That doesn't even mention the adjustment that was made in the example that we just gave you. So if you have some discomfort with real-time risk assessment, you're probably smart to feel so. Here are a few takeaway points. The chemical risk assessment paradigm described in the Red Book has 4 steps: hazard identification, dose response, exposure assessment, and risk characterization. This model was most often used for cancer endpoints. The most significant uncertainties encountered in the model were handled via interpolation or extrapolation from the data points that were available.